In this section, we'll study eigenvalue methods and data mining with considering the Google search engine as an example. An internet search performs two major operations. The first one is traditional text processing. Its goal is to find all the web pages containing the words of the query. In the second step, the web pages must be sorted out. Due to the massive size of the web, the number of hits is likely to be much too large to be handled by the user. So some measure of quality is given to sort them out. And let's see this example. I made a Google search in this stage and using the phrase university. Now, my position is near around Mississippi State University, so that the Google displayed these universities, Mississippi State University on the top, and University of Arizona, University of Washington, Seattle, and so on. And somehow this one is a second. However, anyway, Mississippi State University is on the top. Google knows where I am because Google found and sort those pages and display to me. Along with this query, and at the moment, number of pages are even more than 7 billion. So without sorting, the search engine itself is not really convenient. It must be sorted out for the user. Google uses an algorithm called Pagerank for ranking all the web pages. And Google assigns a high rank to a web page if it has e-links from other pages. And we'll define what e-links are and what our links are very soon. And also we'll see that this self-referencing statement can be formulated mathematically as an eigenvalue problem. For each data mining task, if you want to solve the problem, then you have to design a set of specific mathematical tools. And for this ranking of web pages, Google made some eigenvalue problem so that by solving an eigenvalue problem, Google can sort the web pages very nicely. So this section is showing you a specific example for a specific data mining task. Okay, let's go to Pagerank. This algorithm depends on the Frobenius theory. So let's begin here. Google uses the concept of Pagerank as a quality measure of web pages. The quality measure is, along with this assumption, the number of links to and from a page gives information about the importance of the page. It looks like common sense. Right? Now we'll begin defining the terms that all web pages be ordered from 1 to n, and is the total number of web pages. And I is a particular web page. So you may think that I is the ith web page. Now OI is the set of pages that I is linked to. So our linkers. So in the ith web page, if it includes some other web pages for linking, then these are our linkers. And we are using the NI to indicate number of our linkers inside the ith web page. Now, the set of in-linkers are the pages that have an outlink to I. So in-links means that, and from other pages, for ith one, for other pages, it has outlink to ith one. So it is not easy to see what are the web pages and how many of web pages have outlink to the specific ith web page. However, anyway, we define II for the set of our in-linkers. In general, the page I can be considered as follows. The more important, the more in-linkers it has, because it's more important in outside, and other web pages will make a link, so that the more important, the more in-linkers it has. It's again, it's common sense. However, if we count only number of in-linkers, then it can have some problem. Let's see this one. A ranking system based on only on the number of in-linkers is easy to manipulate. When you design a web page I that you would like to be seen by as many as possible, and you could simply create a large number of useless, for example, informationless pages that have outlinks to I. So that only considering the number of in-links is not really good. So that's the reason we have to change rather than number. Here we try to give a rank for each page, and then now we consider this one. The rank of page ith page is a weighted sum of the rankers of the pages that have outlink to I. Okay, this sentence is a little bit confusing. It can be written mathematically quite clearly. Look at this one. So this is a kind of a preliminary definition. Later on, we'll refine this equation. Now, Ri is ith, okay, is rank for the ith page is now here rank of other pages from 1 to n other pages, that is now weighted sum for each other pages, each of other pages. Now, if there is some outlinks, and so that in this page I is now linked, then now the weight is distributed evenly, and then give some credit to ith one. So that's the equation. The weighting is such that the rank of page J is other pages, one of other pages, is divided evenly among its outlinkers. So that rank is, in a sense, along with even averaging is distributed. So we have to find now such values are rankers. That is the starting point. If you define the PageRank in this way, then it may not be solvable. Look at here the concerns. Now, Q is the link metric. Earlier, you considered this one in square metric of dimension n, and then Qij is here. Once it has at least one link, then it is evenly distributed, and then there's no outlink, then the corresponding column will be zero column. And such metric Q is a link metric, but sometimes it's called the normalized RAM metric. Now, if Q, we consider this Q metric, then over there, that equation has these components there and R, so that this will form metric Q, and there is a vector R, so it's R. So that this, the PageRank equation can be written in this way. Lambda R equals QR with lambda is 1. So R is an eigenvector of Q with eigenvalue lambda equals 0. However, at this moment, it is not clear that this PageRank is well defined because we don't know yet if there exists an eigenvalue of Q equal to 1. So we need reformulation of that PageRank equation. Okay, let's do this one. Now, we'll modify such that and the modification admits eigenvalue 1. In order to do that, we start with this assumption. Assume that a surfer visiting a web page always chooses the next page among the outlinks with equal probability. So that is already here, and this one includes the aspect. Now, assume that the random surfers never get stuck. This assumption violates, in fact, once Q has 0 column, then there's no way to go. So that the model must be modified to satisfy this one. The 0 columns are replaced by a constant value in each position. Because also the equal probability, so that again the value must be a constant. Okay, let's see the mathematical rectification. Define, it's all one vector, the named E, and D is defined in this way. Okay, D is an indicator, and D1 is 1 when the first web page has no outlink. So now NJ equals 0, which means that no outlink, then is 1. So that D eventually becomes the indicator vector for the web pages having no outlinks. Then, and if we define P in this way, Q plus 1 over E, all one vector, and D transpose, then this will make 1 over n for each entry of 0 vector will be filled with 1 over n. So the 0 vectors will be changed, replaced by the 1 over n. And so that anyway, 0 vector is changed into positive vector having 1 over n all the way. So addition of this n entries in each column vector will be 1. So that in any case, after reformulating in this way, P becomes a column stochastic matrix. That means that sum of the entries in each column is 1, and also each entry is non-negative. You learned this one earlier in section 8.7. Now, furthermore, P has this good property. Once you apply E transpose all one vector in left-hand side, then, okay, that's same as here, Q 1 over N E D transpose. So we have that one. Now, along with this one, and it becomes D transpose. Okay, this is indicator for 0 column. So eventually, after simplification, you reach at this one. That means number 1 is left eigenvalue of P. Left eigenvalue, then it becomes automatically right eigenvalue, which means P has eigenvalue 1. Okay, this one is saying that once it is a left eigenvalue, then it becomes automatically right eigenvalue. Let's see here. E transpose P is E transpose. Once it is satisfied, then its transpose is also satisfied. Now, here, so that this equation is the same as that one. However, when you try to find eigenvalues, you have to find the solution of the characteristic equation. But A, for every the square matrix, determinant of A minus lambda I, that is the characteristic equation of a matrix A. And this one is characteristic equation of A transpose. But these characteristic equations are the same, which means that eigenvalues of A and eigenvalues of A transpose, they are the same. And this is 1 is eigenvalue of P transpose, so that 1 is eigenvalue of P. So along with this adjustment, now P has eigenvalue 1. So it's improved. So now we can define the PageRank vector R as a unique eigenvector P with eigenvalue 1, like this. And once we can find our eigenvector of this matrix P, then that's it. However, yet it's not easy. It's not so simple. The question is the uniqueness. The uniqueness still is not guaranteed. To ensure the uniqueness, the directed graph corresponding to the matrix must be strongly connected. In matrix terms, P must be irreducible. However, the given P is not there's no guarantee for P to be irreducible, because now originally from Q, 0 columns are replaced by the column vector and having 1 over n at every entry. But Q, once it is a non-zero column, then some positions, some values are positive, but in many spots it can have 0 values, so that there's no guarantee for P being an irreducible matrix. Okay, here, so that to again, to improve the problem, and we have to anyway modify before the modification will consider Frobenius theory. Eventually, we have to find a technique, a method, such that after modification, the modified matrix could have unique eigenvector for the eigenvalue 1. That's the purpose of this theory, and we have to find a way to modify the given equation. That will be modified. Okay, let's begin the Frobenius theory. We start with this simple theorem. A is non-negative, then spectral radius, that is the largest eigenvalue of A in modulus. So that is eigenvalue, which means that it means non-negative eigenvalue in real eigenvalue exists. And that eigenvalue is the largest eigenvalue of A in modulus, and that is a non-negative eigenvector, and x such that ax is rho A. This is an eigenvalue x. That's beginning theory. Once A is non-negative, then it's guaranteed. So far, it is done because P is non-negative, and so that it's among every eigenvalues, and take absolute value, measuring the length, and then the largest one, but this largest one in magnitude itself, in real number, is an eigenvalue of A. That's this statement. And also the corresponding eigenvector is non-negative. Okay. Now we move one more step. A is non-negative and irreducible. Then, now the same over there, same meaning, rho of A, the spectral radius of A is an eigenvalue of A, but this spectral radius is larger than 0. Over there, it can be 0, but now here it must be positive. And now for this one, here, a positive eigenvector x such that it is satisfied. So that now, once irreducibility is given, then now the eigenvalue is positive, and also the corresponding eigenvector can be positive at all in entry. So that's the result. And also, this is a simple eigenvalue. That means that once you consider the characteristic equation and linearized, then the multiplicity is 1. Okay, we'll go one more step. Furthermore, now it is positive. Matrix itself is positive. Then it's stronger, and also positive matrix itself must be irreducible. So it is, in a sense, the strongest assumption. Then, now everything over there will be satisfied. And furthermore, here for every other eigenvalues in modulus, in magnitude, is smaller than now this spectral radius. So it is a simple eigenvalue, and then from the other eigenvalues are strictly less than the value. To this, we consider this one as, in fact, we are trying to use power method. When you were studying power method, the power method is converging with the ratio between the second largest eigenvalue and the largest eigenvalue. So that now this is the largest eigenvalue, and among these other eigenvalues you can find the largest one, then this ratio is less than 1, so that the power method will converge as desired. Here we have a summary of the theory. A is irreducible and column stochastic metric. Then the largest eigenvalue in magnitude equals 1. And that is a unique corresponding eigenvector R satisfying this inequality. So it's a positive eigenvector. And now one norm is 1, and that means it is a probability vector. Furthermore, A is positive, then all other eigenvalues in modulus is strictly less than 1. 1 itself is the largest single eigenvalue of the given metric. Okay. Given the size of the internet and reasonable assumption about its structure, it is highly probable that the link graph is not strongly connected. That means that the PageRank eigenvector of P may not be well defined. So here, we'll do a little bit of adjustment. Now, the irreducibility is a major issue. It's strongly connected, and then it is irreducible. So we'll try to make the metric entries, all metric entries positive. Then that's it. So that is the idea made by these two people, and Breen and now Page. And they made this idea. So we call this idea $1 billion idea. And practically they got quite similar money from Google anyway. The Google metric is the metric defined in this way. Here, linear combination between P and the metric having all entries are 1 over n, E transpose, and multiply 1 over n, so that you may assume a square metric, and then all entries are 1 over n, and along with this constant metric, now it has linear combination. Alpha will be chosen between 0 and 1. Then original P may have some 0 values, but along with this linear combination, every value in G will be positive. And so that it is irreducible. Now the question is, here, is G a stochastic metric, column stochastic metric? That's the question. We'll check it quite easily. And anyway, alpha is called damping factor. And in Google, and we believe that alpha will be chosen to be 0.85. Later we'll see that. Obviously, G is irreducible because all entries are now positive and also column stochastic. And you can easily check that. And here, furthermore, if you multiply E transpose left-hand side, then along with some algebra, you can recheck this one. That means number one is left eigenvalue of G, which means that 1 is the right eigenvalue of G. So here we can define finally Pagerank equation in this way: GR equals R. So this equation has eigenvalue 1, and this is unique. And also from the Frobenius theory, we know that the largest eigenvalue is 1, and from second eigenvalue is structurally less than 1, because we made G having value, all values are positive. So irreducible, having eigenvalue 1. So eventually, by solving this equation, you can find the rank of web pages. It's really a nice idea, so that really this worth $1 billion. Okay, now we need a little bit of interpretation. In the beginning, the original link metric is modified to get P. That can be interpreted in this way. When a random surfer visits a web page of no outlinks, so there is indicator for no outlinks, the surfer will jump to any page with an equal probability 1 over n. That is adjustment. How about this modification? Although there are outlinks, the surfer will jump to any other page with an equal probability 1 over alpha over n, that portion. Okay, so it's a quite reasonable modification, and also is quite well interpretable, so that it's a really good modification. Along with this modification, the gain is now, mathematically we know that G has unique eigenvalue, the largest eigenvalue 1, and also unique eigenvector. All entries must be positive. That's really good mathematical theory. Here we have a proposition. Let the eigenvalues of column stochastic matrix P be given in this way. Then the eigenvalues of G, along with this linear combination, it becomes, now eigenvalues becomes like that. So even though here lambda 2 length is 1, now after multiplication of alpha, now whole length, this one is strictly less than 1. Right? Okay. In Google linear combination, rather than this one, we may add something else. The vector 1 over n e can be replaced by a non-negative vector, so that it is a sort of a probability vector. And now these entries can be chosen in order to make the search biased toward certain kind of web pages. Therefore, it is called personalization vector. Practically, Google uses a personalized vector. So if you search something, some words, then it can be the Google. Now, the display is quite relevant to you, because by using such a localized the personalization vector, Google is trying to sort, so that eventually you can enjoy better the internet search. Now let's consider the solution of the PageRank equation. We have to solve this equation. Now we know everything about that. Once we solve this equation, then that's it, right? And here the observation is, Google is a full metric, and now it's formulated along with twice of modification. So once you try to the construct G explicitly, then it's so expensive. Okay, here it's full metric, although it is not necessary to construct it explicitly, and represents the number of all web pages, which is order of billions. Nowadays, it is order of hundreds of billions. So it is impossible to use sparse eigenvalue algorithms. And here, the reason is basically some strategy and also some computation time. Only viable method so far for PageRank computations is the power method, the simplest eigenvalue algorithm, but it's best algorithm for the PageRank problem. The rate of convergence of the power method depends on the ratio of the second largest and the largest eigenvalue in magnitude. So it's now that is during the iteration. After k iteration, the eigenvalue, maybe it is approaching to 1, but the difference will be given in this way in order of alpha k. Let's go back to this proposition. Now, that is here, the largest one is 1 for Google metric, and second largest one is alpha lambda 2. So there's a maximum possible value will be alpha. So the solution we write down in this way. Okay. In view of the huge dimension of the Google metric, it is non-trivial to compute the metric vector product. So we'll consider some details. Now, this is recall. The Google metric is defined in this way along with P having these components. Now, Q is the link metric. We consider in this derivation this product. Now, GY, Y is multiplied, and now is output of the metric vector product. The power method is using in each iteration, this product must be done, and here now keep going so that eventually Z, once you do this one again, then the output will approach to the desired vector R. Let's see this one. Normalization free, because G is column stochastic metric, and we can easily see this one. The output over there, and one norm is the same as this one. Now Z is GY, so but E transpose G is the same as E transpose. So the E transpose Y is the same as Y1 norm. So that once start with one norm length 1, then output will be the same. So once you start with a probability vector, then output is the probability vector. So scaling is not necessary. Now, we'll see some more detail for the product. That is G, and Y equals G. And by using the definition here, we end up with these two terms. But beta has these components. So it looks like now D is involved. D is the indicator vector for 0 outlinkers. So it looks like we have to know that. But in practice, in reality, we don't need to define D. We have another way to get beta. Okay. Now, for this equation, we multiply both sides and with E transpose. Then, now E transpose Z is already 1. We start with 1, so that later on is 1 is 1. And we multiply here E to the T. Okay, E transpose. Okay, E transpose. Then that will become 1. Now, that's alpha E to the T QI. And for this one, now E transpose T, okay, E transpose E will become N. So that cancel out. So here we have beta equal 1 minus this one, so that we reach at this equation. But that one is the same as now along with alpha. You can put alpha outside, and now QI here 1 norm. So we reach at this one after finding beta, and along with this one here, we are dealing with only Q matrix. And now QI and alpha, the weighting, and then now beta will be found by using this equation and then put over there and finish to get Z. That's how we can get the product. And also, you don't need to any scaling. The algorithm is normalization free. So we have here algorithm to get the eigenvector R. Okay, now alpha QY is G hat. Okay, alpha QY. There is now alpha QY. That is computed. And now there's Z hat. And 1 norm, 1 minus 1 norm, that is beta. We got it. And now G hat. Okay, that is again, okay, alpha QI. So with alpha QI, there's G hat. And then we, along with this beta, we now update in this way. Rather than 1 over E, we try to put V. It can be 1 over E or the personalization vector. So that update, there is one iteration. And once now, there is, okay, change. We measure the change, and there is a residual. Once the residual is small enough, then we can stop. Okay, that's now G is for the rank vector. Here we have a final note. Okay. Now, we know that the second eigenvalue of the Google metric is alpha lambda 2, and typical value of alpha is 0.85. And so that for the choice of alpha to the k is bounded by 10 to the minus 4, then k must be here 57. So we can guess that Google is using this number based on the report. It is reported to be close to the number of iterations used by Google. From Google report, they say that it's around 57. So we can guess easily, okay, alpha is chosen to be 0.85. Okay, that's the end of the section and end of the chapter. Thank you.